interactive session. So, in the last live session, we introduced the course by discussing the importance of infrastructural growth and development in developing countries like India. We saw a stat showing infrastructural demand and uh, an increase, how it is increasing every year and how it is contributing more and more to the GDP of the country, and what's the goal our nation is targeting with the infrastructural development. However, growth is just one side of the picture. Maintenance of existing structure is challenging, and this has become critical and in recent decades with growing concerns of different forms of deterioration. Now, what does deterioration do? They hamper the durability performance of the structure and reduces the service life to a much lower value than the expected life. And here comes the importance of retrofitting and repair to boost the service life and ensure safe functioning of a structure till desired life period. So you can see here through retrofitting and repair, the service life is increased again. Now, how distresses happen? For that, we went through module A of the course, which discussed about distresses in concrete members. Now, within this, there are seven classification. In related distresses, we talked about corrosion, which is the most critical and happens due to rusting of rebars and followed by expensive stresses generated by a corrosion product. Acid attack we saw in which happens mainly in sewer lines and generates stresses and weakens the concrete. We also saw sulfate attack, which can be internal and external due to gypsum and attringite formation and associated expansion. We saw alkali aggregate reaction, in which we talked about both alkali silica reaction and alkali carbonate reaction, where distresses happen due to gel swelling and expensive stresses that build up inside the concrete. After material related distresses, we talked about distresses due to weathering action, in which we saw freezing and thawing damage, in which pressure buildup because of ice formation. We talked about thermal attack, which is expansion and shrinkage due to temperature gradient, and which mainly happens in pavements. We talked about shrinkage crack, which is due to water loss, mainly by evaporation. We talked about creep due to sustained loading for a long period, which generate permanent deflection. Apart from that, we had little discussion over construction related distresses, in which we saw various reasons which can cause construction related distresses, foundation related distresses we discussed, and some other forms of distresses which includes accidents and natural calamities. Now we ended. So this was all we discussed in first live session. Okay, and we ended our discussion with one pending topic, that was design and load related distresses. So, so these slides shows you the brief overview of material related distresses. First was corrosion, then acid attack, then sulfate attack, and alkali aggregate reaction. And these are weathering actions due to weathering action: freezing, thawing, thermal attack, shrinkage, and creep. Okay, now when we talk about a complete infrastructure, the structure is subjected to different types of loading. So these loadings can be classified into three main types: dead load, which is due to the self weight of the structure; imposed load, which are constantly placed on the structure like furnitures or non-structural elements or devices; and live load, which are moving load like we humans or vehicles. Some other forms of load that are also considered in design also include earthquake load and wind load. Through known standards and provision, we take into account of these actions also. Now, what is the action of these loads? So you can see different types of load acting on the infrastructure. Now, what is the actions of these load? They result in stresses, and there are mainly three types of stresses that we talked about: tensile stress, compressive stress, and shear stress. Okay, so in this image of a bridge, you can see different types of load acting and different stresses generated. So here you can see in the cantilever part, tensile stress at the top, compressive at the bottom. In the mid section, you can see compression at the top, tensile at the bottom, and shear at the edges near the supports. Here you again you can see tensile stress generated due to moving load. In the column pair, you can see compressive stress that is generated due to axial load from above, impact load that can come as water splashes the bridge. Here in the foundation, you can also see dead load and shear load near the support. So these are different types of stresses that are generated within a structure. Now, each structure element responds differently to the acting load. So first we see a simply supported beam, the mid portion here, which you can see. Okay. So here under the action of a constant load, so you can see here a constant load is acting on a simply supported beam. We can see there is compression at the top. So if I visualize it from side, so this is my simply supported beam and this is the load that is acting, and this is suppose the neutral axis. So there will be compression at the top and tension at the bottom. Okay. Since concrete is weak in tension, we provide rebars at the bottom. So here at the bottom, we provide some rebar which can take the tensile load. Now, if there is overloading or creeping, you there can be cracking despite the presence of rebar. So you can see here, due to overloading or creeping or any other like faulty design, or like I didn't provided as much reinforcement as it was required or anything, there is perpendicular cracking that has happened due to loading condition. When the and when these cracking happen, when the tensile stress generated due to load exceeds the tensile strength of reinforced concrete. Okay, so this is the case of simply supported member. Okay, how l- load generates stresses in a simply supported manner and how failure occurs. On the right side, you can see a cantilever beam. It can be a beam or a slab, anything. Now, in such components are present in balconies or chajjas where one end is supported by the column or a slab and other end is free. So in this image also you can see one end was supported by the column and other end was free. Now, and when on these cantilever portion, when some load is acting, so what happens, the top part experiences tension while the bottom part is in compression, like reverse of what we discussed in simply supported member. Now, what can be the problem here? Suppose till now we were placing reinforcement at the bottom. Here also, if we place reinforcement at the bottom, what will happen? This was in compression, this was in tension. So wrong placement of reinforcement or improper design or excessive loading can cause perpendicular cracking at the top part of the member, as you can see here and in this image also. Okay, here the reinforcement was placed there, but still, due to excessive loading or inadequate design, perpendicular cracking happened due to load. Okay, next up can be a continuous member, like a single beam or a slab across eight different support in between and at the end. So you can see this is a single beam or a slab, anything, and there are different supports. Okay, now, here in such element, there can be tensile stresses at both base and the base of the concrete and top part of the concrete. So, near support, the tensile stresses are generated at the top part of the concrete, and in the mid span of the supports, the tensile stresses are generated at the base of the concrete. Additionally, there can be shear stresses near the support which can also act. So, in this image, you can see under the action of load, the tensile stresses are generated here and here, and some shear stress are generated like this. Okay, which are going at propagating at an angle 45 degree till the top face of the member. So how to take care of such member? It should be properly designed, there should not be excessive loading, and the reinforcement detailing should be done properly for top part and bottom part near and away from the support, as well as proper shear reinforcement in the form of stirrups shall be provided near the support and away from the support also. Okay. Next up is a column member. So we discussed it earlier also. Here, due to the load acting at the top, what happens? There are two types of stresses: axial stresses due to load acting, and sometimes bending stresses also if there is some eccentricity. So suppose this is the top view of my column. Okay, and this is my center. Okay, so if my load is acting here, there will be only axial stresses. But suppose my load is acting here or here or here, then along with axial stresses, there can be some bending stresses also which can generate due to eccentricity. Now, when under such condition, what happens? Concrete column can feel distress in the form of bulging. Okay, this is a type of bulging which can happen if the axial load exceeds the column strength, and buckling. So buckling, it can happen if the bending moment generated due to eccentric loading exceeds the column's ability to resist the bending. So in these images also, we can see how buckling is happening here and how bulging is happening here. Okay. Now, under such cases, proper reinforcement detailings need to be provided. Okay. Apart from this, there can be distresses at the joint also in a beam slab, beam column, column slab, anywhere. How? Due to shear forces or due to improper load transfer. So in the images, we can see several joint failure happening, like here. Here one joint failure is happening. Here you can see joint failure. Here also you can see joint failure. And these failures are happening due to excessive loading or improper design. And again, the cure is proper design and detailing. In these images, also you can see horizontal force was happening at the joint and it led to deflection and cracking. And in case of applied load, also if the design is not proper, there can be cracking here. So there can be different forms of failure at joints also, and this detailing is important. Additionally, sometimes we also have pre-stressed members. So, what are these members? So, in these members, to enhance the performance of reinforcement, steel rebars are pre-stressed prior to casting, and then concrete is casting. So, here you can see a steel rebar that is provided tension by and abdomens, and after pre-stressing them, the concrete was casted over it. Okay. Now, when the tendons are freed from the side, what will happen? The steel rebar will bend a little because they were initially uh, provided excessive tension. So, as the tension is released, the rebar relaxes. Now, as the rebar compresses, if the concrete is weak and not properly designed, they can show some forms of map cracking. So, here you can see when the rebar regains its original length, there is a little compression in the concrete also. And if it is weak and not properly designed, it can show some form of cracking near the joint due to excessive shear stress. And you can see the same in the images also, how crack is growing near the joint when the stresses are released. And in this image also, you can see pre-stressing member, and when they are released, how cracking happens. Okay. So again, the remedy can be provided by doing proper designing of concrete and taking care of the released tension force that can act on the concrete member. Okay, so this was all about load associated distresses, why they occur, how different members experience it distresses, and how they can be prevented. Any doubts in the discussion till here?
No, sir.
Okay, so we will proceed ahead then. Okay, so this was all about. Okay, so till now we saw different means of distresses in concrete structure. Now, how we know what are the reasons of distresses? How can we identify these distresses? How can we guess the probable cause of the distress? And further, how can we monitor or say can they investigate the health of a existing structure in terms of has it or how much it has got distressed degraded? So there are a lot of questions. Okay, we till now we have just understood different forms of distresses, but identification, evaluation, and then taking decision also is an important criteria when we talk about repair and retrofitting. Okay, so why these questions are important, we understand. Because they will help us to identify the reason of distress, quantify how critical they are, and decide whether we need to go for repair or we need to end the structure. And if we are going for repair, which action we need to take. Okay, so I hope everyone were clear. This was the brief overview of week 2 content, what we are going to discuss now. Now let's see things one by one. Okay, all the questions that we have just raised, we will answer all those questions one by one. So first thing that we can say first part of this week is to identify the distress in concrete structure. Now distress in concrete structure can be reflected in various ways. These are cracking. It can be minor or major or any form of crack. We will have a detailed discussion of this later on. Second is crazing. So crazing is nothing but development of a network of fine random cracks on the surface of concrete, and this is mainly caused due to shrinkage of the this concrete within inside the surface. The same can be seen in these images also, how a concrete surface is shredded into different pieces due to crazing. Okay. Third is spalling. So it is just a removal of chunk of concrete mainly caused by buildup of tensile stresses inside the concrete cover, and this can happen due to corrosion, sulfate attack, acid attack, or alkali aggregate reaction. We can see one example in the image also, how corrosion of embedded reinforcement has caused spalling of a cover concrete. Okay. Fourth is disintegration. Again, can be due to chemical attack where internal stresses build up at some localized spot which lead to surface disintegration. So here you can see in this images also, there's some surface disintegration happening and how the embedded reinforcement got exposed due to that. Okay. Fifth one is scaling. So scaling refers to peeling or flaking of a concrete cover that has hardened. So after hardening, when the concrete cover peels off. Okay, so scaling is generally a result of significant exposure to freezing and thawing cycles. The same can be seen in the image of a road pavement here. Okay, so mainly it is due to freezing and thawing. Sixth one is dusting. So dusting of concrete is like a powdery or chalky substance that forms on the surface of concrete. Now why it forms? It is caused by the hydration of cement and water. So when cement and water reacts, they form a hydration product, which on surface can appear like a fine powder, which can be easily blown away by wind or rain. Now, dusting of concrete can also be caused because of evaporation of water from the surface, which has led to improper hydration, which can leave behind white powdery substance. So here in this image also you can see dusting, which has happened maybe due to evaporation of water. Okay. And seventh one is pop out. So these are like tiny, often cone shaped depressions in a horizontal concrete surface, and they mainly occur due to expansion and fracture of a near surface aggregate, and how these aggregate fail due to expanding gel formation due to alkali aggregate reaction. So this image you can see a pop out happening in between a road, and this can happen due to alkali aggregate reaction. Okay. After pop out there is honeycombing. So honeycombing is a result of improper curing, improper compaction, faulty formwork positioning, or early removal of formwork. Anything can result in this, and the image shows a column having honeycombing due to improper compaction. So what can happen? Our concrete is very stiff. Now we have poured it inside the formwork, but we have not provided proper compaction. So due to that, what can happen? My concrete may not be able to flow everywhere inside the formwork and cover everything, and thus when we are removing the formwork, we can see such honeycombing patches on the surface of concrete, which resulted due to improper compaction being provided. Okay. After this, the ninth one is buckling. So we have seen buckling column due to excessive loading. Another reason of buckling can be due to thermal expansion. So here you can see a pavement where thermal expansion led to buckling. Okay. Then we have seepage, the tenth factor. There can be several reasons behind seepage uh, in concrete, like poor graded aggregate being used, overdose of admixture, deviation from designated design, improper concrete placement, impurities in aggregate, all can be responsible for water leakage in concrete. And one of the uh, in the images you can see one of the concrete wall showing damp patches of water due to seepage. Okay. After this we have delamination. Again, after effect of expansive stresses that build up inside concrete, mainly due to corrosion, or it can be due to chemical attack. Okay. Corrosion we have talked in detail, discussed earlier also, and can be seen in the form of appearance of rusting stains on the surface of concrete with longitudinal cracks aligned in the direction of reinforcement. You can see here the rebars got exposed and some rusting stains here, and here you can see which was the effect of corrosion. Here also you can see some brown rusted stains. And finally, it is we'll talk about erosion. This can occurs due to two main reasons: abrasion, which is nothing but wear and tear of concrete surface, and mainly seen in pavements where due to vehicle movement there is rubbing of surface. And one more place where erosion can happen is in the concrete wall lining supporting a water flow, where cavitation damage can occur due to irregularities in the flow of high velocity water. Okay, so in the image you can see one example of abrasion of a road pavement which occurred due to wear and tear caused by vehicle movement. Okay, so I hope everyone are clear with these different identification of distresses. Now, there were total 13 distresses, 12 of which we have discussed, and the first and the most foremost distress that we left for discussion was cracking in concrete. So, cracking in concrete is a very complex distribution. Okay, it can occur before concrete hardens due to several reasons like foamwork removal, subgrade movement, shrinkage, or settlement. And it can happen after concrete hardens due to several reasons like thermal stresses, chemical attack, weathering action, drying and shrinkage, overloading, creep, subsoil settlement. Any of these can be reason. Okay. Now, the cracks in concrete can be classified into two categories: structural crack and non structural crack. So, structural crack are those which result from improper design, overloading, foundation settlement, faulty construction practices. So, these are all the major cracks, okay, which are occurring during the design of phase of the structure. Now, these cracks can be seen in any orientation. It can be horizontal, vertical, diagonal, and even like a step. The same you can see in the image also. Here is a vertical crack, horizontal crack. On the floor you can see a diagonal crack, a step cracking. These are all a form of structural crack, and since these are major, they can endanger the safety of a building. And apart from structural cracks, there are non-structural cracks, which are minor cracks, and they result mainly from chemical attack, shrinkage, and weathering action. Like we can see in this image also, various location of structure shows different minor non-structural cracks. And since these cracks are minor, they may or may not endanger the safety of a building. Okay. Apart from these, cracks can also be classified as active crack, which are live and expanding with time. The reasons can be due to overloading or weathering action. Dormant cracks, which have already been occurred and won't propagate further. One reason can be shrinkage. Other classifications can be isolated crack or pattern crack, and we have seen such cracks in a lot of discussion till now. Okay, so I hope everyone are clear with the discussion of cracking and different forms of distresses in concrete structure, how we identify different distresses. If yes, let's see a simple question now. Okay, so here I have four pictures of distresses in concrete, and you need to identify the reason behind the distress. Any doubts?
Yeah, good evening. I have a small doubt. Some cracks has been observed on the concrete surface that is a minor nature. So how do you distinguish both the crack which structural cracks and which is for sinkage crack?
हाँ,
Suppose some sinkage cracks also developed.
Hmm.
So as per code, it says that more than 3 to 5 crack is the structure, maybe structural crack. You
Hmm.
need some analysis.
Yeah.
So during visual inspection, how do you decided that which type of crack is appearing on the surface of the concrete?
So basically, during visual inspection, also when like the people who inspect this cracking, they have like a gauge, a thickness gauge. They use that also sometimes to detect whether it is a non-structural or structured crack. And basically, when we talk about visual inspection, we know the history of the structure, what is the exposure of the structure, what can be the problems in the design of the structure also. So based on that also we can guess whether this crack is a structural crack due to faulty design or something, or it can be a non-structural crack based on the exposure conditions. These are all like these classification properly one can do based on the crack width. Okay, or we can do through inspection also. We can comment later on whether it was a non-structural or structural crack. So it all like there's a lot of overthinking or like ahead thinking that we need to do before classification of a crack. But right now I have given a major distribution, like when structural crack happens, what are the major reasons, and when non-structural crack happens, what are the main reasons.
Okay.
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 So let's see this question now. There are four images, and you need to identify the reason behind the distress in these four images. Okay. So I will wait for a couple of minutes. I will mute myself. You think about all the four images, and then we will discuss.
Sorry, is the session on, sir?
Yeah, it is on. Yes, yes, it is on. Okay, let's see the answers now. Okay, someone has answered. Okay, first one, step cracking due to uneven settlement, differential settlement. Yes, it is correct. In the image 2, pop out, which is happening due to thermal stresses. Yes, it can be correct. Third is overloading. It is a like a brick wall with a concrete cover on the top. So overloading might not be the reason. We will see. Okay, and final one is transverse cracking. Okay, foundation settlement. We'll see the answers. Okay, so let's see one by one. So in the image one, we can see step cracking. Okay, so these are step cracks, and these cracks mainly happen due to foundation settlement, which can be due to differential settlement also. Okay. In the second image, we can see buckling of pavement that may result from thermal stresses which are not being able to get released from the side, so they led to buckling of the top layer. Okay. In the third image, we can see a spalling of concrete cover over a brick wall. So you can see a underlying brick wall, and over that a concrete cover was there. Now this can occur due to contraction or expansion in the building materials also, which resulted from fluctuation in temperature or even moisture content. So you can see some moist patches that was there here, also some moist passage, so that can be also be some reason behind this form of cracking. Okay, and in the final image we can see some form of transverse cracking that is happening. So this is a like a true image of a Qualzua Spanbay bridge. Okay, there's a bridge named as Quanzhou Spanbay Bridge, which was built in 2008, and during the use of the bridge load increased, and the girders there on the girders the crack appeared in these forms, and it was reported that these cracking was due to large amount of traffic and loading of vehicles on the top. Okay, so this is a true report of a structure. Okay, everyone are clear with all the four images and the reason behind them?
Yes, sir.
Okay, so let's move ahead now. Okay, now we know. Now, to know the state of an infrastructure, it is very important to evaluate the current status of infrastructure in terms of its deterioration level. Okay, so there can be several ways to evaluate a infrastructure. The first and the simplest way is visual inspection. Okay, so the purpose of visual inspection, what are the purpose? It is the most versatile and powerful non-destructive testing. It is typically the first step of assessing a concrete structure, and the goal is to identify visible signs of distresses, defects, and deterioration. Okay, and what it reveals? So it reveals surface cracks, spalling, or scaling if there is any discoloration in terms of rusting stains. If we can see efflorescence, if we can see staining, if we can see uneven settlement or deformation, if there is step cracking due to that, or even corrosion and reinforcement if some part of reinforcement is getting exposed. So we can see in the image also how just from the image we can identify distress and cause of that distress. So you can see here exposed rebar being located at different locations and spalling of concrete which can happen. So we can comment that this was due to corrosion of embedded reinforcement. Now based on the exposure condition, if it is near seashore line, we will say corrosion was due to chloride attack, and if it is away from shoreline, we can see it may be due to carbonation of concrete. So ahead we can assess the carbonation depth of the concrete also and give a strong justification over the defect. Okay, now visual inspection report also includes a lot of important information about the infrastructure also, like construction year, layout, previous repair if they were done, material used in the construction, number of stories when we talk about building, type of foundation of the building, type of bridge, if there is a bridge, number of piers and girders. All these informations are also necessary when we talk about visual inspection, because these information helps us to decide what can be the reason behind the crack. Okay, these information along with the initial visual inspection that we conducted helps us to decide whether to go for further testing, any form of further testing, non-destructive or destructive, and also whether to conduct or give any final statement of the structure regarding its future action. Okay, so the only limitation of visual inspection is it can only give visual surface, only visible surface can be inspected, and internal defects may remain unnoticed. So based on the initial look, we decide whether to go ahead or not and quantify the data. Okay. After visual inspection, we have semi-destructive testing. So, what are the key points of these testing? So, these testings are equipment-based testing, and they are intended to assess the in situ performance of the concrete. So, in visual inspection, we just did a qualitative surface look of a infrastructure. What is the status of the infrastructure? If we want to go in deep, we need to go for some testing. So, these are in semi-destructive testing, we assess the in situ performance. What is the live performance of the infrastructure? Okay, since these are semi-destructive, they may cause some localized damage of the structure, which needs to be repaired after the testing is done. And this damage, though is sufficient small, may or may not cause loss in performance of the structure. So generally, semi-destructive testing do not cause loss in any performance of the structure, because we are taking we are testing a very small portion of the infrastructure. Okay, so the images also reflects these critical points in the order of action. So here you can see a semi-destructive test conducted on a concrete column. Here you can see a wall in from which core is taken, and here you can see after core is extracted how they are measuring some dimension and everything. Okay, we will see in a simplified manner. So there are four major semi-destructive testing categories for concrete. These are pull out and pull off test, penetration resistance test, core sampling and testing, and carbonation depth evaluation. So in the course content, carbonation depth was in NDT, but since we are drilling concrete and taking sample out, it should be in semi-destructive testing. Okay, so we will see in a simplified manner each testing one by one. Okay, so first is pull-out testing. So in this, so the aim of this test is to estimate the in situ compressive strength of the concrete, and it is based on the principle that the force needed to extract the embedded metal inserted in the concrete is directly proportional to the compressive strength of the concrete. Okay, so by measuring the pull-out force, we are correlating it with the compressive strength and commenting what is the strength of the infrastructure. Okay, so, how this test is carried out? So, in this test, a metal disc with the enlarged head is inserted into the concrete surface till a predefined depth. Two bearing rings are placed on the sides of this metal disc at equidistance, and these rings, what is the function of these rings? They provide a path for the crack to propagate and ensure a conical failure. So you can see here dotted line, which shows how the failure will happen when this will be pulled out. Then a loading system is placed over the metal disc using a screw, and a force is applied to pull the metal disc out, and ultimate pull out force is recorded. The same process can be seen in the images also. First, a screw head was installed, then our pull out machine was fixed over it with three loading reaction rings, or we say bearing rings. Slowly, this screw was pulled out by applying mechanical force from the top, and here you can see how failure is developing. And once the pull out is conducted, you can see a conical failure happened on the surface. Okay, now, how we quantify? First, we calculate the apex angle, the angle at which the failure happened. Then, we calculate the pull-out strength by dividing the failure force recorded with the area of frustum. And finally, we relate the pull-out strength with the compressive strength of concrete. Okay, so pull-out can be done in on both newly cast concrete and in place concrete. For newly cast concrete, it is called log test. Okay, where a metal disc is pre-installed in the concrete and later pulled out after desired period. And this test is performed under the guidance of various predefined codal provisions. Okay, so this is done on newly casted concrete. And for existing concrete, pull-out test is known as capo test, in which permits performing pullout on existing structure without the need of any pre-installed insertion. The same we saw in the previous slide also, where first we insert a screw with the expanded head and then we pull it out. Okay, using a force, supplying force. Okay, so later this pull-out strength is correlated with compressive strength, and one of the figures you can see here. Okay, so in this figure, you can see the pull-out strength on the axis and the compressive strength on the y-axis and how they are linearly correlated. Okay, so let's see one numerical here. Okay, so it is given that the diameter of steel that was inserted was 16 mm. The embedded length of the insert in concrete was 200 mm. The apex angle was 30 degree, and the load that was applied to pull out was 40 kilonewton. And we need to calculate the capo pull out strength. Okay, I will place this. Okay, this is not needed. Okay, you just do the calculation once. How we will get the pullout strength. Okay, calculate the area of frustum first and divide the pullout load with the area of frustum and then calculate the strength. Okay, I will wait for 1 minute and then we'll see the answer. Okay, so let's see the solution now. So the first step will be to calculate the area of the insert. Okay, now for this we need apex radius. Okay, and how we can calculate the radius? So what is apex radius? Let me draw it. So this is our failure pattern. It is in the form of a cone. So for calculating this area, this is our area of cross section on which the load was applied. Okay, on the side we need this radius. Okay, how we can calculate this radius? This complete is apex angle alpha. So this is alpha by 2, and we know the depth, embedded length of the insert, that was L. Okay, and the diameter of insert also. So we can use the diameter of insert also, anything we can use. So apex radius will be given by Apex radius r will be given by d upon 2 tan alpha by 2. Okay, so this will come out to be 16 divided by 2 times 10 15 degree. Okay, and on solving you will get a value 6.93 mm apex radius. Now once we know the apex radius, we can calculate the area. So area will be area of this part above, area of circle, that is pi r square, and this slant area which is nothing but pi r times d, r times l. Okay, no, r times d. Okay, so area of the insert A will be given by pi 3.14 times r square 6.93 times 6.93 plus r times d. So 6.93 times, it should be L. Okay, 200. So upon calculation we will get, just wait a second, 4502 mm square approximately. Okay, and then step 3 will be strength. So pull out strength will be nothing but force upon area. So it will be 40 into 1000 divided by 4502. So it will come out to be 8.88 Newton per millimeter square. Okay. So this is how we calculate the pull out strength. When we know the pull out force from the testing and we know the apex angle of failure. Okay. If we don't know the angle of failure, we can always use this equation to calculate the failure angle also. Okay. Any doubts? Just try to solve this question on your own also once again and you will be clear. Hmm. If there are no doubts, we'll move ahead.
So could you please explain it again?
Uh, the screen is visible, I guess. Please share the screen.
Yes, sir, it is visible, sir. Could you please explain the problem once again?
Okay, so first we calculated the apex radius. So apex radius is given by this formula. Once we know the radius, we calculated the area of failure. So it was a conical failure. So we need to area will be the slant area of the cone plus the area of top. Okay. So this, since this was the part of concrete which was acting, which was experiencing load, so we will calculate the total area of that part. And once we know the area, we will calculate the strength. The strength is nothing but failure load upon area. Just
Sir, it would be always in a conical shape, or it can be in different
no, it will be in a conical shape because of these reaction rings that we have inserted. So these rings are inserted to make sure that the failure is conical. So the design of pull out machine is such that the failure will be conical only. And though it won't be a proper cone, but we generally assume it as a conical failure. So in the image also you can see. Here also you can see. Here. Everywhere it is a form of conical failure.
okay, sir.
Okay. Let's move ahead then. Now next is pull off testing. So the aim of this test is to estimate the in situ tensile strength of concrete. And on what principle it is based? Tensile strength required to pull a metal disc from the surface to which it is attached is directly proportional to the compressive strength of concrete. Okay, so in this test, a metal disc is directly attached on the surface of concrete with the help of an epoxy adhesive, and then this attached disc is pulled out by applying a force. And the force at which the contract breaks is recorded as pull off force. So in the image, you can see this device which is used to pull out a metal disc. So there will be a like cylindrical metal disc, and this disc will be attached to the concrete surface using epoxy adhesive. Okay, and later on, this instrument, pull off testing instrument, was used to pull this metal disc out. And here you can see a certain failure, how the when the disc is pulled out, how it appears. Okay. Now, sometimes if the concrete surface is not uniform or if it has incurred carbonation, what can happen? The surface pullout may not happen properly, or the value may not be accurate enough. So, for in such cases, what we do, we drill a little bit from the concrete, we do some partial coning in the concrete, and then we conduct the pullout test. So you can see here the pullout was conducted on the surface, and here you can see pullout was conducted after some partial coring. Okay, and the recorded pullout force is used to calculate pullout strength, how we know the area on which it was acting, and then it is correlated to compressive strength. So here in this graph you can see the pull off test tensile strength and the relationship with cube compressive strength. Okay, so as the pull off tensile strength increases, the compressive strength of concrete also increases. Now, apart from estimation of compressive strength, one more application of pull-off can is to check the bonding between two layers. So suppose I have done some plastering over the concrete. I want to know how properly the plastering has happened over the concrete. How is the bond between the plaster and the concrete? So in such cases also pull-off is conducted. So in this, what is done? Again, using an epoxy adhesive, metal disc is attached, and then this disc is pulled off, and the pattern of failure can comment on the effectiveness of a plaster concrete bond, like we can see in the image also. Here in the first part, failure happened in the substrate, so we can they say the plaster's concrete bond was much stronger than the concrete, so plastering was done properly. Here the failure happened at the interface only, so it just happened at the interface, in which says that concrete strength was more, and the weakest link was the interface of plaster and concrete. Here the failure happened in the overlay material, in which can be plasters, which says that the plaster strength was lower than the interface strength and the concrete strength. And here nothing failed, the complete just the disk got removed, which shows that all the strength are adequate. Okay, and just the bonding is proper and the materials are proper. Okay, now the third semi-destructive testing is penetration resistance testing. Okay, so the aim of this test is to measure the hardness or the penetration resistance of concrete, and it is based on the principle that penetration is inversely proportional to the compressive strength of the concrete. So based on the depth of penetration, we can correlate with the strength of the concrete. Now, this test can be conducted in two ways. Probe penetration, where a metal probe is made to penetrate through the concrete surface using a gun driver, and the exposed probe length is measured and correlated with the compressive strength of concrete. So in this image, you can see in the first image the probe gun and the measuring device. Here you can see one person inserting the probe inside the concrete wall, and this is the correlation of the exposed probe length with the 20-day compressive strength of concrete. Okay. And second is pin penetration. So in this, a metal pin, a small metal pin, is mechanically compressed into the concrete using a spring, and upon reaching the maximum possible extent, the pin is removed, and the penetration depth is recorded and correlated with the compressive strength. So this is the setup for pin penetration. Here you can see pin penetration being conducted on the concrete wall. It is mechanical driven inside the concrete up to maximum extent, and when this device is removed from the concrete, the depth of pin penetration is measured, and that is correlated with the compressive strength of concrete. Okay. The fourth semi-destructive test is core sampling and testing. So this is the most reliable testing which gives the best correlation with the in situ strength of concrete. Okay, the testing has two main aims. First, to determine the in situ compressive strength of concrete, and second, to carry out some chemical analysis or petrographic examinations if needed. Okay, and it is based on the principle that cylindrical concrete core is a lab scale representation of the structure. Okay. Now, for taking the core out of a structure, the equipment that is used is core cutter with a diamond impregnated bit. So here you can see the in the image a core cutter with a bit, and how it is squeezed inside the concrete and how you used to take the core sample out. Now there are quite a few things that need to be taken care of for proper core sampling. These are that the cutter should be placed rigidly and drilled perpendicular to the surface. So here you can see in this image, this cutter is placed rigidly and perpendicular to the surface. It is preferable to take core from the middle portion and avoid edges so that there is no breakage in the core when it is taken out. The reinforcement shall be avoided, okay, when the core is taking out. So you should know the proper position of reinforcement, and then you should take the core out. Cracked area shall be avoided since it will hamper the testing of concrete. The core diameter as per codal provision should generally fix between 100 to 150 mm so that we can replicate the casting that we do of say, concrete cylinder in the lab. And the length to diameter ratio is generally fixed around 2. And once the core is taken out, it should be properly stored in saturated condition so that it is under constant hydration. And so the surface shall be grinded and capped with gypsum prior to testing so that surface is even before testing. Okay, so here you can see in this image one core sample being taken out from the concrete surface and how it is stored properly and prior to capping and testing. Okay. Now, post collection, finishing, and storage of concrete, the cores are tested for compressive strength using compression testing machine as shown in this images. For carrying out compression testing, the loading rates it's fixed. So for cylindrical core testing, the loading rate is 14 Newton per millimeter square per minute. Upon reaching the ultimate failure load, the compressive testing machine will stop applying the load, and thus, with the known cross section area of cylinder and the failure load, we can estimate the compressive strength of the core. Now, sometimes correction factors are also needed to be applied in case there is some variation in core diameter or length. These factors are listed like here. So, first correction factor is based on core diameter. So, if the diameter is in this range, the correction factor is this, and if it is lower than this, the correction factor is this. And based on the L by D ratio, the correction factor is applied like this. So, suppose I have my value was 50, and this was the diameter variation was in this range, so I will multiply this value with 1.03 to get the actual value of the strength compressive strength of the core, and accordingly we can apply this correction also. Okay, now along with strength, the pattern of core failures shall also be recorded, since as per IS 516. The assessment of failure pattern is also important for core testing, and you can see in this images also unsatisfactory failure of cores can be seen in these ways, while satisfactory failure of cores can be seen in this way. And these are also important when we give a comment about the status of a core and the strength of the core. Now, apart from strength estimation, the collected core sample can also be tested for various microstructural properties using petrographic examination or even chemical attacks, using various chemical analysis like chloride content, sulfate content, and all. We'll brush up these things later on when have a discussion about petrographic examinations. Okay. The fifth and the final semi-destructive testing is carbonation depth measurement. So the aim of this is to measure the depth of concrete which is affected by carbonation, and it is based on the principle that CO2 penetrates and react with calcium hydroxide to produce CaCO3. As a result of this, the depassivation occurs due to lowering of pH, which increases the corrosion rate. Now, we have talked about carbonation when we discussed carbonation induced corrosion, but for estimate, so we won't go in depth regarding these relationships and all. For estimating the depth till which carbonation has happened, phenolphthalein indicator is used. So phenolphthalein is a pH indicator which changes color from pink to colorless, then the pH drops below 9. Okay, so when this indicator is sprayed over the concrete, it can show various regions where carbonation has occurred and carbonation has not occurred. And for measuring depth, there are two ways. Either we can collect a concrete core from the structure and spray phenolphthalein on it and see the depth of carbonation, like in this image, you can see. And one more way is to drill a hole inside the concrete, spray phenolphthalein, and record till the depth where it is uncolored portion. And that uncolored portion depth will give us the depth of carbonation front. So, like we have this concrete, okay, ignore this. We have this concrete. We are drilling inside the concrete and we are spraying phenolphthalein, and we are seeing when till where we can see the color change. Okay, so till the spot where we see pink coloration is there, we say it has not been affected by it has retained its alkalinity, and when the pink color disappears, we say that the zone is getting carbonated. Okay, the same can be seen in the image also. I hope everyone are clear with the semi-destructive testing. Any doubts still here? If not, we'll move till to the non-destructive testing part. Any doubts? Okay, let's see ahead now. Okay, after semi-destructive testing, we will now discuss non-destructive testing. So the key features of these testings are: these are equipment based testing, which are intended to assess the in situ performance of concrete or infrastructure. They doesn't cause any damage as the name suggests to the structure, and generally more than one test methods are required to for are correlated for reliable estimates. Since these are non-destructive testing, they are not that much reliable, and thus they need to be carried out, like multiple tests need to be carried out for final prediction of the state of the infrastructure. So in the image also we can see various entities being performed on various structures, on wall, on base slab, floor slab, or on a cylindrical pipe. Okay, with and these testing are performed without damaging the structure in any form. Okay, within NDT there are five major testings. These are rebound hammer, ultrasonic pulse velocity, electromagnetic cover measurement, half cell potential, and resistivity measurement. We'll see each of them one by one now. Okay, so first one is rebound hammer testing. So the aim of this test is to measure the hardness of concrete, and it is based on the principle that harder the concrete surface, more will be the rebound number. And this helps in determination of compressive strength by relating the strength with the rebound number or surface hardness. So this test is performed using a, Schemidt's rebound hammer as per the codal provisions of IS 516 Part 5. And what makes this test suitable for site inspection is that it is inexpensive, quick, and simple. So you can see in the first image a rebound hammer being operated on the concrete wall. Now, how this is operated, what is the science behind this its operation? So a basic rebound hammer consists of a hammer and a plunger in a spring-loaded mass system. So initially the hammer along with the plunger is compressed against the surface of concrete, and once the spring is completely compressed, the hammer and hammer is lying steadily and perpendicular to the surface, the hammer is released. Now, upon releasing the hammer, what will happen? The hammer will rebound, and the amount of rebound will depend upon the elasticity of the medium. So, more is the strength of the material, higher is the elasticity, and thus more will be the rebound number. And this is related with the compressive strength for predicting the strength of the infrastructure. Okay. Based on the location of the structure, rebound hammer can be conducted in three orientation: vertically down, vertically up, and sideways. So for if we are assessing a deck slab or a floor slab, we need to go for a vertically down orientation. If we are assessing a concrete wall, we can go for a horizontal orientation, and if we are assessing a roof slab, we can go for a vertically upward orientation. And generally, 10 to 15 readings of rebound numbers shall be taken before accurately estimating the compressive strength, before correlating it with the compressive strength. And in this image, you can see how, for different orientations of testing, how rebound number is correlated with the strength. Okay, so since in vertically up orientation the gravity may increase the amount of rebound that can happen, so that's why its value is lower than horizontal orientation. And similarly, for vertically down testing, since gravity is opposing the motion of spring after releasing the hammer, the value is higher than the horizontal orientation. Okay, so I hope everyone are clear with how with orientation the strength correlation is changing. Second entity is UPV testing. So the aim of UPV testing is to quantify the in situ, qualitatively assess the in situ concrete in terms of uniformity and integrity. So it is based on the principle that wave velocity depends upon elastic property and density of the medium, and higher the UPV value, more dense and uniform the concrete is. So the test is performed as per the guidelines mentioned in IS 516 Part 4, and it is suitable for site inspection due to its since it is inexpensive, quick and simple. So in the first image, you can see a UPV test being operated on a concrete column. Now, what is the science behind this testing? So a UPV test consists of two probes. Okay, these are two probes. These are known as transducers to send signal represented by T and receiver to record signal represented by R. Now, what makes these probes unique is that they are made of piezoelectric material. So, what does this mean? Piezoelectric materials are those which can convert mechanical energy into electrical energy and vice versa. So, initially, electrical pulse is generated using the UPV device. These pulses are fed to transmitting transducer. The transducer convert the electrical signal into mechanical waves. These mechanical waves pass through the material and reaches the receiver. The receiver converts the wave again into pulses, and time of flight or the duration of measurement of this wave flow is recorded. And based on the distance between the probes and the time of flight, the UPV is calculated. V is equal to L by T. Okay, simple formula. Okay, so if there is any internal crack or void in concrete, the wave will take more time to reach the receiver, and thus the UPV value will be lower since the time is increasing, so velocity will decrease. Okay. Now, similar to rebound hammer, a UPV can be conducted in three orientation depending upon the accessibility of a structural element. It can be direct method where both the phases of a structural element are accessible. So direct method is direct transmission of wave from one end to the other. Indirect measurement in case of walls or columns on at the sides. So here transmitter is here and receiver is here, and this will be my part length. And indirect method, these are conducted on walls or base floor slab. Here transmitter is here, receiver is here, and my part length is like this. Among these three, the most reliable one is direct method since it will cover the whole area of concrete. Okay. Now, based on the recorded UPV value as per IS code, one can comment on the integrity of structure as if my UPV value is above 4.5 kilometer per second, we say the concrete quality is excellent. If it is between 3.5 to 4.5, we say the concrete quality is good. Between 3 to 3.5, we say concrete quality is medium, and below 3, we say concrete quality is doubtful. Okay. So I hope everyone are clear with the discussion of UPV and rebound hammer. If yes, let's see some theoretical question related to rebound hammer and UPV that will make you think more about the process of action of testing and how to take care of them during site inspection. Okay. Any doubts in the discussion of UPV and rebound hammer? Okay, so I will mute myself for a couple of minutes. You just go through the questions. I will show them on screen and think what can be the reason and type your answer in the chat box if possible. Okay, so let's see the answers now. First question is, what will be the effect of reinforcement on the recorded UPV value? Can anyone answer? Okay, so since reinforcement, due to the presence of reinforcement, my UPV value decrease, may increase. Why? Because steel is has more density than concrete. So if my waves may can propagate faster through steel and reach the from transducers to receiver, it may reach faster. So the value that we get of time of flight may be lower than the actual value, which can give us a wrong indication of the integrity of concrete. Okay, so in such cases, what we need to do, we need to take a proper correction factor being associated when there is reinforcement present near the UPV testing, or if possible, we should avoid the reinforcement area. Okay, the area where there are reinforcements. Okay, now second is, what is the effect of moisture content?
Sir, please repeat the first question, please, sir. Sorry, I
Okay,
missed it.
what will be the effect of reinforcement on the recorded UPV value and why? So we know reinforcement is more elastic, steel is more elastic than concrete, and it has higher density than concrete. Okay,
Yes,
now
yes.
I have a concrete block like this, okay, and there is steel rebar here, and I have my transducer here, okay, and my receiver here. Okay, now I am sending waves here. So if my waves propagate through steel, what will happen? Its speed of propagation will increase since it is more elastic medium and it has higher density. So actually my time of flight should have been T1, but due to the
To
presence of steel, my time of flight will reduce. Okay.
reduce.
So if my time of flight will reduce, my UPV value will be higher than it should be, and it may give
Right.
us a wrong indication about the quality of concrete. Suppose my UPV was supposed to come out between 3 to 3.5, and it went up till 4 due to the presence of reinforcement. So in this way, reinforcement can affect. So how to take care of this? Either by considering proper correlation factor correction factors when there are reinforcement near the testing area, or avoiding the presence of reinforcement. So in the code there are proper guidelines. It is mentioned, if my reinforcement is at this much distance away, then UPV may not be affected. If its orientation is along the testing or perpendicular to testing, how we can take the corrections and how we can like improve the value. Okay, clear? Okay, so the second question is, what is the effect of moisture content in concrete on UPV and rebound hammer value? So we know uh, density of solid is more than liquid and it is more than gas. So if my voids inside the concrete are filled with fluid, what will happen? My time of flight will decrease compared to it was what it was when there was air filled voids inside the concrete. So my UPV value will decrease. Okay, my UPV value will increase. Okay, in case of there is moisture in concrete. And when we talk about rebound hammer, the concrete moisture we know has a direct impact on the compressive strength of the concrete. Okay, so we say a moist concrete cube has a lower compressive strength than a air filled concrete cube. Why? Because water is incompressible. Okay, now if my concrete is moist, what will happen? My rebound value will also decrease since my compressive strength is decreasing. Okay, and it is generally said that it is the rebound value decreases by 20 to 25% when we compare moist concrete sample with the air saturated concrete sample. Okay, so these are the figure in which the rebound hammer value decreases due to moisture. Okay, now third question is, what happens to UPV and rebound hammer values when concrete is carbonated, and which one is more reliable in this case? Okay, so when concrete is carbonated, what will happen? My voids that were there, which contain calcium hydroxide, now calcium hydroxide doesn't provide any strength to the material, okay, to the concrete. Now upon carbonation, it converts into calcium carbonate. Okay, so if my, which is a solid precipitate and which is filling the pores inside the concrete. So if we will do UPV on a carbonated concrete, we will get a higher value than a non-carbonated concrete. Okay, so on a bulk scale, if we are conducting UPV, we may record a higher UPV value compared to non-carbonated concrete, since the voids are now filled by calcium carbonates and they will provide a much easier path of wave propagation. Okay. Now talking about rebound hammer, suppose my surface is getting carbonated and I am conducting rebound hammer on it. So what will happen? It may give us a higher rebound number than it should be. So we may get a wrong prediction of the compressive strength of concrete, because rebound hammer gives us the surface strength of the concrete, not the bulk strength of the concrete. Now if my surface is carbonated, my strength will be higher as per the rebound number, but actually the strength was not that high. So rebound hammer may give a overestimate value when the concrete is carbonated. Okay, and thus for carbonated concrete, it is important to conduct both UPV and rebound hammer so that we can check properly what is the status of the concrete. And generally, UPV is more reliable than rebound hammer when we talk about carbonated concrete, since UPV is giving us the whole bulk look of the concrete, while rebound hammer just give us the surface property of the concrete. Okay, final question is, what is the effect of surface condition on UPV and rebound hammer value? So suppose my surface is not uniform. What will happen? My UPV won't be conducted properly. The wave propagation will be disrupted because of this. And that's why we use gel. Okay, we use a capping gel to ensure that the UPV, the contact of my probes are proper on the surface. And similarly for rebound hammer also, if my surface is not uniform, then my the hammer won't be steady and it won't be perpendicular, and this can hamper the reading. So if my hammer is like this, due to gravity action, my rebound of spring may get affected and it may not give us the actual value of rebound. So that's why it is said that when rebound hammer is conducted, my hammer should be perpendicular and steady. Okay. So this is the effect of surface condition. I hope everyone are clear with the discussion.
Yes.
Okay. Now the third entity is electrochemical cover measurement. So the aim of this is to determine the location of steel reinforcement and depth of concrete cover, and it is based on the principle that the presence of steel may affect the electromagnetic field. And the direct action of this is the detection of free rebar and the depth of free rebar. Now, on what principle it is based? So it is based on the principle of electromagnetic induction. So using a power source, the electric field is generated in the primary coil, and this electric field is made to reach the secondary coil. Now if there is no ferromagnetic material detected, so what will happen? The potential difference between these electric field will be negligible and my output reader will show a low value, okay, a zero value. But if there is some ferromagnetic material like steel inside the concrete, what will happen? Due to the presence of electric field, it will also get charged and it will produce its own magnetic field, and this will cause change in the magnetic field sent by the primary coil and the magnetic flux recorded by the secondary coil, and the change in flux will cause some potential difference which will be recorded on the output device. So in this image you can see this is the coil setup, which consists of two coil, primary coil and secondary coil, which is attached to a power source and a measurement device. And here you can see in this image how a person is operating this device to locate the depth of the reinforcement. Okay, so maybe upon increasing the strength of the signal, the depth of till which this flux are going is will increase, and it will be used to detect the depth of the rebar. Okay. After this, the fourth entity is half cell potential measurement. So the aim of this testing is to predict the likelihood of corrosion in embedded reinforcement, and it is based on the principle that higher is the corrosion rate, more will be the electron flow. Since more is the electron flow, more negative will be the potential with respect to reference, and higher will be the corrosion probability. Okay, so this testing is based on ASTM C716 part 2015 codal provision, and it is only applicable for uncoated reinforcements. Okay, so what is the science behind this testing? So we can imagine two half cells. So we may have seen this diagram earlier also, la- in some different cases also. Suppose there are two half cell, okay, and there is electrolyte solution in both the half cell, and these two half cell are connected by a salt bridge. Okay, now one electrode is anode, which has a higher tendency to corrode, and the other one is cathode, which has lower tendency to corrode. Now, due to difference in potential of anode and cathode, what will happen when I will collect the anode and the cathode? I will record a current flow, and voltmeter will help us to measure the change in potential which at which the current is flowing, and this system will be balanced by the flow of ions through the salt bridge. So this will complete the circuit. So here the electrons are flowing, here the ions are flowing, and my circuit is getting completed. So this is the concept behind the half cell potential device. Okay. So voltmeter is what records the potential difference between both electrodes, and which indicates my potential of anode. So suppose if I fix my cathode to a inert material, anything that I will record on the voltmeter, I can use it to calculate the potential of anode, and I can predict what is the corrosion at anode. Okay, so in this image you can see this is my reference electrode. It can be of copper sulfate, or uh, AgCl silver chloride electrode, or calomel electrode. So there are different kinds of reference electrode. The aim of reference electrode is that it should be stable and its potential should not change. Okay. Now when this reference electrode is placed over the concrete, and one end of the connected with one end of the voltmeter, and other end of the voltmeter is connected to the reinforcement, my concrete will act as an electrolyte. There is copper sulfate here also. So this circuit that we talked here is inside this anodic circuit is this, and we are connecting it with a voltmeter, so we can record the potential difference between the reference electrode and the reinforcement steel, and this potential difference will give me the value of corrosion potential of my reinforcement, which will help me to predict the probability of corrosion inside the reinforcement. So here you can see one person conducting a half cell measurement on a concrete column, and based on the measured potential we can predict the probability of corrosion activity as, if my potential is less than minus 200, more than minus 200 millivolt, we can say the probability of corrosion is less than 10%. Minus 200 to minus 350, we say the probability of corrosion is uncertain, that it can be between 10% to 90%. And if my value of recorded potential with respect to the reference electrode is more negative than minus 350, we say that the corrosion probability is more than 90%. Now this value will change based on the reference electrode also. So right now these values are for copper sulfate reference electrode. If we are changing the reference electrode, these values will change, and in the code, this code, the range of those values are mentioned. And using, if we will move this probe across the concrete column, we can also plot counter maps of different location and what is the probability of corrosion in those locations. So this can also be used to detect uniform corrosion or localized corrosion if it is happening inside the concrete. Okay, so just read this steps one again. Try to understand the salt bridge discussion that I did here, and correlate that discussion with the diagram here, and you will be clear with the half cell potential. Okay, after half cell, the fifth and the final entity is resistivity measurement. So the aim of this testing is to measure the resistivity of concrete against ion flow, and it is based on the principle that ionic flow through concrete will happen across the least resistive part. So more are the voids inside the concrete, lower will be the resistivity of concrete. Now, resistivity measurement is generally carried out using two devices. There is two-probe resistivity measurement, which is known as resistimeter RM8000. This is also a mean by which we can measure resistivity of concrete by applying this instrument on the surface of the concrete and measuring the resistivity. And the most commonly used one is Furner's 4 probe resistivity meter, in which low frequency current is applied across the outer probes, and potential is recorded across the inner probe, and based on the ratio of potential and current and the length of flow, the resistivity value is estimated by the device. Okay, so in this diagram, you can see the circuit which governs this testing. So across the external probe, the current is supplied, and across the internal probe, the potential difference is recorded, and the resistivity is given by 2 pi a by 2 pi a into v by I. Okay, so a is the distance between the probes, which is generally fixed as 50 mm. V is the recorded potential and I is the applied current. Okay, so VA and I are generally recorded by the device itself, and since A is fixed, my device will directly give me the resistivity value. Okay, which is given by represented by rho. Okay, now this is surface resistivity. Here we saw surface resistivity. One more form of resistivity can be bulk resistivity, where two plates are applied across the concrete core sample, and across this plate potential difference is applied and the current flow is recorded. Okay, so in these images you can see concrete core being taken out, plates are applied across the core, and potential difference was applied through these metal plates and the current flow was recorded. Now, based on the concrete resistivity value, one can comment on the corrosion risks also. Since lower will be the resistivity, higher will be the chances for ions to flow through the concrete, and higher will be my corrosion risk. Okay, so you can see lower resistivity, higher is the risk of corrosion, and as the resistivity value increases, my corrosion risk reduces. Okay, I hope everyone are clear with the discussion of these three testings. If yes, try to answer these three questions. I will mute myself for a couple of minutes. You also think if you have any doubts in the three testing we discussed, and if not, try to answer these questions. How can we identify carbonated concrete in visual inspection? Maybe in visual inspection you may not identify carbonation has anchored inside the concrete, but through some semi-destructive testing you can inquire carbonation. Or one more way, if my concrete is carbonated and the carbonation depth has reached till reinforcement, what will happen? My corrosion will initiate. Due to corrosion product will form, and that will give some rusting stain on the surface of the concrete. Now, if you see some rusting stain on the surface of the concrete and your infrastructure is located very far away from the shoreline or any area where chloride attack can happen, you can say that carbonation might have occurred inside the concrete. So you can just guess, but to actually check whether carbonation has occurred, you can go for a semi-destructive testing there only. So based on the distress that you see on the surface of the concrete, you can guess what can be the possible reason behind the distress and which testing I need to do. So, like when there is corrosion, you see longitudinal cracking along the reinforcement direction. So, if you see those cracking, you can guess which you can like predict what can be the reason behind that, and then you can evaluate whether it is true or not. Okay, just try to answer these three questions. I will mute myself for a couple of minutes and we'll see the answer. Okay, so let's see the solutions now. What are the questions? First question is, what will be the effect of moisture content on the resistivity of concrete? So when we talk about concrete, ionic flow happens through fluid filled voids. Since ions penetrate through concrete by dissolving in fluid. Okay, so if I will have air voids, what will happen? My ionic flow won't happen to the voids, it may happen to the cement paste or the aggregate. Now my aggregate and cement paste are generally more resistive than the water. So when my voids are filled with water, what will happen? It will provide an easy path for ionic flow to happen, and thus, due to moisture present in concrete, my resistivity value will reduce. So you can see there will be several literatures which would have commented on the relationship between resistivity versus relative humidity of concrete. So as the moisture content in the concrete increases, my resistivity value decreases. Why is surface resistivity preferred over bulk resistivity? So there are two reasons. Okay. First, bulk resistivity involves semi-destructive testing. So you need to take one core out of the infrastructure and then you need to place two plates over it and you need to record the resistivity. Okay. Which makes it less desirable compared to surface resistivity. Another reason is I am applying some voltage across the core. Okay, this is my positive terminal, this is my negative terminal, and my current is flowing through the concrete. Okay, now concrete is not conductive, it is an insulator. Okay, now since it is an insulator, my signal strength may decrease as it goes from the positive terminal to the negative terminal, and thus it is not possible that every time I will be able to get a constant value or a repeated value when I test a bulk when I do a bulk resistivity, since it may hamper my single signal strength and I may not be able to go for a larger core. Okay, maybe the length of core can also affect this reading, or everything can come into account in such cases. So that's why surface resistivity is preferred over bulk resistivity. Why wet sponge is necessary in half cell potential testing? So we said when we were talking about half cell potential, this is my probe reference electrode and it is connected to a reinforcement. Okay, now here my one half cell is this, where I have a copper sulfate solution, suppose, and second half cell is my reinforcement and concrete. So concrete is acting as a electrolytic solution. Now I need wet sponge so as I can improve the conductivity of ions from reference electrode till reinforcement. Since if I won't use wet sponge, what will happen? My ionic flow won't be proper. So the value that I am recording on the voltmeter may not be accurate. So that's why wet sponges are used and recommended in code before testing, so that ionic flow can be properly transferred from the reference electrode to the concrete electrolyte. Okay, so I hope everyone are clear with the discussion that we had today. Any doubts in the discussion today? Any doubts to anyone? If not, we will conclude the session today. So, in today's session, we first had an overview of load and design associated distresses in concrete structure. Then we talked about identification of distresses in concrete structure, in which we talked about 13 types of distresses and focused in depth on cracking in concrete. Then we talked about inspection of existing infrastructure, where we talked about visual inspection and its importance. Then we discussed several semi-destructive testing, which include pull-out and pull-off, penetration resistance, core sampling and testing, and carbonation depth measurement. And then we talked about several non-destructive testing, which includes rebound hammer, UPV, cover measurement, half cell, and resistivity. Okay, so this was all for today's session. Thank you.
Thank you, sir.